Good morning, everyone. We can start the actually Friday seminar series, but today is Tuesday. But thank you very much for your flexible scheduling, Gillian. So I want to introduce today's guest speaker, Gillian Abe. She is now retired and visiting research scientist with the Applied Geodynamics Laboratory at BEG at here, having worked with a team over the last decade. She held an MA in natural science, earth sciences from the University of Cambridge and PhD from the University of Liverpool, where she studied the impact of structural basin, floor topography, and turbidity, turbidity currents, and the stratigraphy of the deepwater system. During her 33-year long career in the oil and gas industry, she worked for Shell, BP, and BHP, and various experience for Gulf of Mexico and Northern North Sea. And she is a classic sedimentologist and stratigrapher with expertise in deepwater reservoir search sediment interaction and deepwater fold and thrust belt. Her current research interest focused on deepwater turbidite stratigraphy and reservoir variability in structurally active basins. And also, she is a co-director of Uphill Geoscience Company, and she teaches field classes in Haute-Provence in France. So please welcome Gillian Abe today. Whenever you're ready, you can start.
Thank you so much, Wonhin. I will now share my screen, and it'll just take 2 minutes to get it sorted. Right, share and share. Okay, everyone, can you see the screen?
Sure.
Good, that's actually a good sign. And secondly, can you see the laser pointer?
Yes.
Yep. Lovely. Okay, so welcome everyone, and thank you for making the rapid adjustment from last Friday to today. Short notice on all sides. Thank you, Jennifer, for making this happen. So first of all, I'd like to acknowledge Western GECO for a beautiful data set over the Central Gulf, deep water. And we have used it extensively over a number of years, but we now don't have access to that data anymore. Okay, so we also want to thank the RPS Nautilus Training Alliance. Hang on a minute, I'm just going to shut the door. Any extraneous noise here? Okay, because, well, they have allowed us to use a figure from the N112 handbook, which is a training class that Stan and I lead. And we'll be doing that again this year. And the other people I want to thank are AGL, first and foremost, and particularly the Minibasin Madness team, which was Ollie Duffy, who's now at Chevron, Nayara Fernandez, who is with GFC in Germany, and Chris Jackson, and Frank and myself, and also to the GBDS team for dating of the mapped surfaces. Very helpful indeed. We had a good collaboration going with them, and we still do. So finally, thank you, Mike Hudek, who is the most patient PI I know. And this is Frank here, and me, in a remarkably astute cartoon by Randall Munro. Thank you, Stan. Here's to many more years of working together, and our PhD student, Xiaodong Yang, and Donald Christie, who's responsible for all the upgrades of OnLapse 2D, which you will see today. So the study area is in the deepwater US Gulf of Mexico, and it's within this area here. And we'll be comparing it with our outcrop analog, which is the Grey Dano deepwater clastic turbidite system in Chaloufie in the southeast of France, where there are turbidity currents that have deposited a thick succession of clastic sediments onto a structured depositional slope, as in here. And as everybody knows, this is a global problem. This seismic is from somewhere in West Africa. But today we're going to look at a case history from the Gulf of Mexico. And you will see structural maps and amplitude maps of this surface, which is what we call the 400 surface. And they are slightly rotated because for anonymity, the Western GECO wanted us to rotate the maps. So this is the present day structure of a clear, unambiguous extinction event. And it is Trim A, which is a very famous benthic forum in the Gulf of Mexico, which is currently, I believe, dated at 0.74 million years. And that's from the GBDS database. So it's a surface that's reasonably easy to correlate from the continental rise out here back onto the lower slope mini-basin terrain. And it's one with significant stratal onlap in the structured mini-basin terrain up here on top of the salt canopy. That's the Sigsbee salt canopy. That's the younger Pleistocene salt onto which Pleistocene sediment is deposited. The 400 surface is a very good hiatus. It's a time of low sediment flux, and the structural activity during that hiatus, both salt withdrawal and sliding, gravity spreading down the slope, actually has given rise to significant and complex three-dimensional surface relief on top of the salt canopy. The important structures are developed here on top of the salt canopy. These folds are at the downslope edge of the canopy, and the lower continental rise in front of the salt is actually relatively unstructured. Please note that the frontal structures have actually grown considerably since the 400 surface, but the patterns of uplift and subsidence have remained the same in the study area. So keep an eye on the frontal fold belt here, which is on the cross section here, and this area here of extension, which corresponds to this area on Frank's cross section of extension on top of the canopy, and it detaches onto the salt canopy here. And we'll come on to what that is later. So we're going to focus on a relatively sand-rich fairway within our overall study area. And our data is on the margin of the major Paleo-Mississippi sediment fairway of the time. And it's for this reason only that we're able to study the interplay between structural activity and the sediment flux. Because here, the slope is grading in terms of sediment relatively slowly. If you go into the main sediment fairway, where the slope is grading rapidly and prograding, the structural signal is so much more difficult to decipher. So having put ourselves in a mega-regional context, let's move on to examine the sandier fairway that bursts onto that 400 surface. And this is a summary of what we're going to talk about here. So the grays are the structural surface, and the yellows and the fawns are the depositional pieces, elements that we have examined. The regional slope is from top to bottom of the slide here, and the turbidity currents that flow from the shelf margin down the slope into this lower slope area are influenced by local topography superimposed on that regional slope. So this is a beautiful, if somewhat gory, frequency decomp display of the 400 surface. And unfortunately, work was curtailed for a couple of reasons. One is that the data was returned to Western GECO, and that was fundamental. But even prior to that, we're going to do a little more, actually slicing upwards from the 400 surface. But PaleoScan, which is the software we were using, is actually challenged in this frontal fold belt area and in other areas where there is a high degree of structural complexity with a lot of erosional unconformities stacked on top of one another. So we've got a slight problem here that the surface that you map on top of the salt has no point where you can go out onto the continental rise and an automatic system actually recognize it as the same surface. That has to be done manually. And I would say hats off to Frank Peel for not only correlating between mini basins that were isolated, but also getting that correlation so precisely off into the continental rise. And you'll see how precise that is with some of the depositional elements. The seismic amplitude response is here, which is what we're going to be looking at henceforth. And that's from the map surface itself. And it represents, because of the frequency of the data, about 50 to 100 meters of stratigraphy. And the expanse of bright amplitude response is rare in the Pleistocene of our study area. It expands over a good-sized area and has multiple depositional elements. It's confined in what is quite a thick sequence, the 400 to 200, we call it, but it's confined to a very narrow interval right at that 400 surface, and we'll come to why later in the talk. The line interpretation you see here in this map is of the stratal elements that I could identify, with the numbers referring to the examples I'm going to show in this talk. And I must remind you that I will also refer to this inset here with the structural topography that's being generated by structures that are on that 400 surface, and in particular, the frontal folds and this area of subsidence at the back here, ahead of that extensional breakaway fault, which began its activity at the 400 time. Yay. So while we were interpreting the deposits on this surface, we were increasingly struck by the similarity with another deep water system, my analog, also responding to topography in deep water fold and thrust belt on salt, the Grey Danotte, which outcrops in southeast France. And I've included some photos of the outcrops, which should provide you with a visual analog, at least, of what we are actually interpreting in this seismic amplitude map. Interestingly enough, the mini basins on this terrain here are very similar in scale to that which we see in the Anot system too. So the first area we're going to look at is this broad syncline salt withdrawal basin here, number one. And it's a salt withdrawal basin behind the frontal folds here. And the earliest deposits actually lap onto that first of the frontal folds here. And the deposits are mixed, low to moderate amplitude, and they largely terminate behind the frontal fold belt. And you'll see quite a few strands of what look to be channels, and overall the system looks distributary. So here it is, and here's that surface in here. Okay, so the architectural building blocks in this area are interpreted as terminal lobes by me. The mixed low to moderate amplitude response would be consistent with these being a stack of distal lobe deposits, likely containing reservoir sands, but of mixed quality. And we see here at Bro, which is a section in the Grey Danotte Basin very close to Anot itself, where we see this similar distal terminal lobe. And here it comprises stacked, thick and moderately bedded debrites and transitional flow deposits. The flows entering the basinal area expand onto the reasonably flat topography, very similar in scale to what we see in our study area, and deposit rapidly as the flows encounter the topography of the opposing frontal folds, which you can see here. And in the case of the Bro outcrop, the on-lap surface is here. It looks like a down-lap surface, but actually because of further structuring, what was horizontal turbidites here are actually down-lapping. They were originally on-lapping onto a structured surface, which again was a fold in the Southwest Alpine Foreland Basin. As the topography is infilled, or was infilled, the lobes were progressively incised. These gullies here in red. Gullies developed and they converged to pass through a perch low between two strands of the compressional fold, here and here, in the fold belt. The high amplitude deposit here is actually between two of the frontal folds, and it's relatively high amplitude. It's almost certainly sand rich, but it's again limited by the second ridge of folds, which is right at the front of the canopy, in the perch minibasin on the frontal fold belt. So the flows will accelerate as they go through that incised gully there, and likely deposit better quality sand in the confined basin on top of the frontal fold belt, hence the high amplitude response. On the continental rise in front of the salt sheet, the 400 surface is a low amplitude reflector here with no internal character, and it almost certainly comprises the finer grained elements of silt and mud that are deposited from the upper parts of the flows entering the frontal fold belt. Flow stripping is highly likely at this stage, and only the upper cloud of fine-grained sediment can reach the continental rise in front of the salt canopy. The basal parts of the flow are trapped behind in the topographic low here. And we have a very similar situation at Le Rouge, which is at the northern end of the Anot syncline, which again is confined at its northern end by folds. And this is deposited right up against the slope of one of those folds. You can see the on-map here. Oh, just to go back one though. And what we see here is similar flow stripping. These are sharp-topped sands, and there are no fine-grained caps whatsoever. Interestingly enough, there's a lot of hummocky cross-stratum here, which we believe is related to the generation of internal waves in the turbidity current at this slope. But you don't see the fines preserve. The fines go on further north into another basin, which we'll come to later. So in summary, the flows initially terminate in the broad syncline of the salt withdrawal basin, but progressively, erosive gullies develop a connection with perch synclines on top of the frontal fold belt. Flow stripping ensues, and sand is confined to the mini basins on top of the salt, and only fine-grained material is shed into the continental rise in front of the Sigsbee. Now let's move east. So that's where we were looking before, here. Now move east to this area, to two folds, here and here, that are at 90 degrees to the frontal fold belt. There's a tight syncline between them here. And here the amplitude response is moderate to high. This is a cross-section through this basin with these two salt ridges here. And the bright amplitude is literally confined to the syncline, the tight syncline between them, the lowest part of the syncline. A good analog for such deposition is in a structurally confined low that is here at Anot itself. This is a section parallel to the axis of a very similar scale syncline, where the flows run into the syncline from the south towards the north. And the syncline itself has a plunging axis that opposes the flow, which this one does too, because it's actually plunging away from the frontal folds. So this is what we anticipate here in our seismic example, where the syncline meets the frontal fold belt, striking across the trends of those tight salt cord anticlines. So flows entering the syncline are forced to deposit their bed load rapidly, very rapidly, potentially. Here at Anot, what we see is thick, amalgamated, sand-rich reservoirs, and we may anticipate the same in that tight syncline on our seismic data in the Gulf of Mexico. In the analog, there are no mudcaps preserved. We have sand on sand, not entirely due to erosion. Again, the finer grain parts of the flow are able to surmount the topography. So once more, it is a confined system, but not a ponded system. The same is highly likely in our seismic example, where flows will be confined by the structural topography and retain energy despite losing bed load. So we see evidence that the flows are not ponded by the topography at this stage. There are tributary gullies which cut through the fold belt and converge to pass through a single notched exit point in the frontal fold. And the low amplitude area in front of the incised gully, slope gully, does have a very distinctive amplitude variation associated with the linear thick on the lower continental rise in front of the canopy. And this is interpreted as a levade channel, which grades downflow of the incised gully and is fines dominated. And the sandy bed load of all the flows is still confined here, up dip, behind and on top of the frontal folds. So in summary here, the lateral flows are confined in the tight topography of the syncline and remain energetic here. But because they cannot expand, they're in that tight syncline. But they still have enough energy to flow up the opposing slope and onwards through, in the case of our Gulf of Mexico example, through gullies into the continental rise. The flows have better capacity to surmount the topography, but they still dump their load behind the syncline or in the syncline behind the fold belt. So only the fines are carried on forwards. And what we see in our example is, in the analog example, is at the next subbasin down, what we see are thin-bedded turbidites. And if I'm lucky, we're actually going to see that this little picture blown up. Yes. Thin-bedded turbidites that characterize the base, a very thick set of thin-bed turbidites characterizing the base of the succession in the Grand Collier area, beyond the Paleo High. Okay, now it gets really interesting. In this area here, the amplitude response is highest of all, and the pattern is counterintuitive. The high amplitude follows the trend of the first syncline at first, and then it hooks round into a second, equally tight perch syncline that connects through into this broad area low here. The structurally confined fill of the perch syncline connects into a subsiding basin, and the trajectory actually opposes the sense of the regional slope, which is from north to south. The high amplitude would suggest that the fill is sand rich. So why is this trend hooking round and opposing the slope? Well, what we have is a structural reason for the trajectory of that basin fill. The subsidence in the hanging wall of this breakaway extensional fault is at the head of an obstructed mini-basin and actually creates an area of subsidence, we think, into which the flows are actually dragged into this broad syncline, which is here in the hanging wall of this extensional fault. So what's super interesting about this is that in order to understand why we get subsidence here, we have to understand this whole structural section. What has happened is these mini basins to the north have actually collided now with relief on the base of the salt. So they've collided with sediment that's underneath the salt and welded effectively tight, and they now can't move as easily up that ramp and into the area of the higher level of the Sigsbee canopy. So what happens is the area in front of that actually continues to slide and expand down slope. And what you get is a series of extensional faults breaking away from the rest of the slope up dip. Very interesting. The activity on that fault actually starts at 400 times. So the tight syncline is likely to have plunged northwards towards that hanging wall subsidence early in the sequence, close to the 400 surface when the structural topography was at its maximum. So how did the flows respond? Well, there is a surface here on the amplitude map against which other trends like this are actually truncated. So it's possibly an erosive surface. And to the right of that surface and through the tight J hook, the amplitudes are brightest of all, which would suggest we have really good quality sand there. We see this in our analogue at Anot, in the confined syncline we saw earlier, this time looking as a strike section with the paleocurrent flow going into the photo. Here we see a major erosive cut, and the sands above and below are quite different. Below are the massive, poorly sorted and amalgamated sands we saw earlier, through which the people were walking. And above, what you see are clean, well-sorted sands, here, with scour and fill structures indicative of deposition from supercritical flows, which are very, very fast, and that leads to standing waves and cyclic steps, made famous in a series of references by people like Mathieu Catigny. The turbidity currents are doubly confined here in Anot and also in our J-hook syncline by the erosive scour or channel and the tight structural syncline. And so they accelerate, and the best quality sands are in bed forms reworked by multiple flows. Finally, as the sand degrades at the exit of the tight syncline, and we see no evidence of that anymore, it's intersected by a through-going channel here, which captures the topographically confined drainage and exits the front of the canopy through a deep canyon. That channel has actually come all the way from the mid-slope, and it's capturing our drainage now and taking sediment out onto the continental rise. Well, the analog at Gronkoye is a very coarse-grained erosional channel, which actually isn't seen on this cross-section. I think I've corrected myself now, Stan. By an erosional dominated channel complex that deeply incises into an earlier lower net to growth section. So in summary, sand is delivered across the still structurally confined basin floor, likely in a doubly confined structural and erosive setting, depositing the best quality sands, which are good quality reservoir sands, in these last stages before capture by a through-going drainage system arriving from the mid-slope. Once capture occurs, sand is now delivered to the lower continental rise, and active sand deposition in the mini-basins on top of the canopy is doomed. So drainage is successively captured by long-distance channel systems emerging from the mid and upper slope out of our study area, like this one here. Very soon, a single strongly aggrading channel system, this one, oh, actually, no, another one, nearer the Pleistocene play fairway axis over here to the east, captures all the drainage, even this. And the majority of the stratigraphic record of the 400 to 200 sequence is actually dominated by that one channel complex. Once that happens, sand-rich deposition ceases in our study area, and the older depositional elements close to the 400 boundary are abandoned and draped by fine-grained silts and muds. Hey, stratigraphic trap potential, which is true of every Pleistocene depositional sequence, so that overall, the Pleistocene slope itself is very mud-prone as a result. So in summary, let's just have a little look at the healing phase in 9 slides. First, second, third, fourth, fifth, fourth, fifth, out onto the basin, and finally, a slope channel coming in from higher up the slope. So what have we learned? We've seen that salt movement creates topography during times of low sediment flux. When the sediment flux increases, the surface topography decreases, And the topographic healing phase is very laterally variable. So as the depositional slope is re-established through erosion and aggradation, then other channels break through from the mid and upper slope and capture all the drainage. The early systems are abandoned and the majority of sand is confined then on to channel complexes. Conclusions. Well, the first, because I work for the Applied Geodynamics Lab, salt is complex. Salt is also viscous and responds over very long time scales. The structures at depth matter. So when that basin collides, as it does here, a whole new set of structures develop. We would call that a structural threshold. And those thresholds are actually very important in terms of producing bathymetry on the sea floor. Structural tipping points. Salt moves, whoops, I'm just going to change my pointer so that I can actually activate Tim Dooley's wonderful model here, physical model, upon which we rely always. It moves not only downslope, rapidly often, over quite long distances, but as you will see, these basins actually rotate too, because the salt is being diverted around other obstacles, and so salt moves in 3 dimensions. And if we're to understand the distribution of sand close to salt, we must document more examples of the stratigraphic response in 4D, both in space and time, and relate them to specific salt structures, mechanisms, because the fill and spill is never 2-dimensional. So I'm now just going to go briefly onto another little related but slightly separate topic, which is accommodation space versus rate of sediment accumulation, which we've alluded to earlier in the talk. So far today, we appear to have been talking about the infill of an apparently static topography, or have we? And how do you tell? So the criteria we often use to establish deposition on an actively deforming substrate is inference from major slope remobilizations, slides, slumps, and MTCs, although you've got to watch out, your MTCs could be coming all the way from the shelf edge. Obvious stratal wedging and multiple unconformities existing throughout the section with internal off-lap and on-lap. Evidence of turbidity current reflection and deflection off slopes throughout the stratigraphic section. And we see all of those features here at the Mutterkopf-Gossau Basin. And these are courtesy Doug Patton, who presented a poster with us at a conference in 2017. So what about this example? Are the structures forming the basin floor bathymetry in this case quiescent? Not necessarily. This is actually Stan Stanbrook's PhD study area of the Grand Coyer subbasin, and you see incredible on-lap at the base. But after that, after a very short period of time, the succession is effectively a grading without internal on-laps or off-laps. No discernible internal unconformities or wedging strata. The succession simply aggrades. And the facies associations do change upwards, but they're largely in the upper part of the section in response to changes in the depositional system rather than the topography itself. And any slope remobilization is actually confined to the lower parts of the succession. So what might appear to be a fundamental difference between these two basins in terms of structural activity is actually related instead to the sediment flux in the basin. And I'll show you this on the next slide. So where you have a relatively low sediment flux, the surface topography builds relatively slowly relative to the structural topography. And what you do in these left-hand examples here is maintain structural bathymetry all the way through the succession. But as you increase sediment flux, then the structural relief becomes subdued. And at a certain tipping point, in this case a stratigraphic tipping point, then the sea floor topography is successively buried. And in fact, under the load of the sediment on top of that salt, you might actually see a suppression of the salt rise, as we often see under the weight of that load and the strength of that load. But that tipping point is absolutely critical and can define the difference between the Mutterkopf example and the Gossau example and the Grey-Danner example. So here, a long, long time ago, there was an atwater discovery in the lower slope of the deepwater fold belt in the lower Miocene. And the oil-bearing reservoir was seen to dramatically thin onto the structural high from the basin center here, where thick, high net to gross but wet sands of the same age were observed. And in addition, the oil-bearing reservoir was highly deformed, and entire sections of this stratigraphy are actually inverted in the core. And we believe remobilization is from the actively growing structural high here. So what we're seeing is, once again, you're actually seeing the topography during the lower Miocene in this area maintaining pace with a slightly lower sediment accumulation rate. In the lower Miocene, that is. In the lower Miocene, this part of the fold belt had a lower sediment flux than this part, where fields like Mad Dog are developed, and the sediment flux was higher, and the structural relief was rapidly buried and leaving sands accumulating over both the highs and the lows, much to the joy of the exploration and development geoscientists in Mad Dog. And this is carried on to the present day, but at the present day, we actually have the flip side, where we're actually seeing now the western area has significant seafloor bathymetry and represents the isopack beneath very well indeed. Every low is actually an isopack thick. And this is a low sediment flux area compared to this, where the modern day Mississippi is focused. And in this region, you see little or no expression of the subsurface isopack whatsoever. So the salt withdrawal and any other gravity spreading and gravity sliding structures are completely subdued by the depositional and erosional topography of the Mississippi fan itself. And any variations in facies associations that you see across this region in the east are entirely related to the processes going on the fan, which is aggrading and prograding rapidly. And I just wanted to say thank you for your time. And do we have any questions or comments? And I'll stop sharing. Complete silence. Okay, you can ask to unmute if you wish, and if not, then thank you very much for joining me.
I don't see anything in the chat, Jill. Does anybody have any questions for Jill?
I have.
Do you want to unmute yourself?
If I may.
Thank you, Greg. I'm glad you understand it. Doesn't surprise me at all.
Hello?
Hello? Who am I? Oh, hi, Gerardo.
Oh yeah, can you hear me well? Because
I can hear you.
With the microphone. Just a quick one on the part one. I'm not sure if it's entirely a question, but so the deflection that we see towards in the latest phase,
Yeah.
the deflection that we see towards the northeast.
Yeah.
You alluded to a fold and creating some area of some depositional area in there. But it wasn't clear to me if that deflection was an interplay of the fault and also the evolution of the structures as you elucidated on your second part. And I was just wondering, have you thought about trying to quantify what was the main factor in the faulting or just some salt evolution? Thank you.
Absolutely. Well, the salt evolution and the actual structure I referred to as the extensional breakaway kind of go hand in hand. But interestingly, Nyara actually did an analysis of the fault activity and showed the growth on the faults that occurred or started pretty much at the time of that 400 surface. And in terms of the relative speed of development of that topography, it's faster than the development of the salt withdrawal itself, which is a much, much slower process. The salt is, as I said, viscous, and it responds over a really quite long time periodicity, whereas the fault, once the basin to the north got obstructed, then the gravity sliding process is actually pretty fast, and the breakaway extension, Nyara was able to demonstrate, happened pretty rapidly at that point and very much began at the 400 surface, developing quite a big area of subsidence behind the folds we've been talking about. And so we believe, and it's always worth studying in more detail if we have the data, which we don't now, but if you have the opportunity, it'd be worth actually looking again at these kinds of relative rates between gravity sliding and spreading and the salt withdrawal. My own belief, and Frank might like to comment here, is that from this example alone, we were actually able to demonstrate that fault was moving much faster than the salt was withdrawing. I do get my tongue in a bit of a twist here. Is that okay for the moment? And if you want to come back to me with an email discussion, that's no problem.
No, that helps. I just thought that it was quite interesting. I was wondering why exactly they're, closer to
if you are interested in that topic, please do go and talk to Mike Hudek, because it's quite, in fact, any of the AGL people. There's a series of talks that were given in and around the 2018 era that are actually related to obstructed mini-basins and the response of the whole of the set of structural mechanisms in that area. So it was quite a big focus of the mini-basin madness group at the time. So please do go and talk to those who are still with the group, Mike and Tim, and anyone you can find.
Absolutely, thank you. Yes, I have with Duffy.
Okay.
Thank you. I've spoken to the team. Thank you.
So Eric, hi.
Another question from Carlos. Can you, if you don't mind,
no problem at all. Sorry, I just looked at the bottom. I don't know why I did that. Carlos, so if he's not going to say it, I'll actually read it out. Is there any well control?
Yeah, Gillian, thank you. Yeah, thank you very much for
Basically,
well, if you have
said,
any well control, for some.
Actually, I meant to say right up front, there is calibration in the region. There is no calibration in that particular set of mini basins, and it's really frustrating. Actually, in the abyssal plain, there's not the abyssal plain, actually, the continental rise immediately in front, there is again calibration, but not there. And it's really frustrating that we don't have more shallow penetrations of at least the Pleistocene. But we do have good calibration of the age dates, but not of the lithologies. And we need many, many more studies like this that relate the structural processes to proper lithology. And I wonder whether Carlos actually noted, like we did, that there's a lot of low amplitude, they look like blocks in this interval. And it does look as if there's quite a bit of debris associated with some of these deposits. And of course, there are other things that can cause amplitudes, as all the geophysicists in the room will have been well aware of. But in this case, we have other calibrated examples where amplitude in the Pleistocene does respond very much to sand. Pleistocene in some places can also respond to volcanoclastic material, which has been, or was early in the days of exploration, a real drilling nightmare because we'd end up with porosity in the volcanoclastics, but not permeability.
Thank you.
Okay.
There are one message to Gillian,
Thank you.
and then
Oh,
Eric
David
Scott.
Mulligan.
Eric,
Okay, Eric, can you actually ask your question? Can you?
Yeah, sorry. It was just
there you
just noticing you had going from the J hook, that was with the brightest amplitude, with the implication showing that is the greatest sand with your model.
Yeah.
But then it goes into that other channel system,
Yeah.
well, on whatever it is, that other sediment pathway that
Yeah.
has much lower amplitude associated
Yeah.
with that. And obviously then that means that I'm just going to, figuring out where the sand goes, where it's going to be deposited. Now we got implying that's a whole different gradient system to there, different accommodation being incorporated into that sediment supply system. And where does the sand go?
Right. Well, that particular J-hook amplitude is eroded, and it's eroded by the base of what then becomes the dominant capture system. So that capture system does head straight out, straight across the 6B, straight out into the continental rise in front, and that's the beginning of the end. So literally that J-hook system taps into and then is progressively even more eroded by, but I believe it probably tapped into it at that point, in fact. So the system that it cuts across it on the east is actually coming from the mid-slope. So it's an evolution we see quite often, is that you see deposition all the way out in the slope at the beginning of a sequence, but it's not organized. But once that mid-slope gets organized, or more importantly, once the upper slope starts to heal and the mid-slope starts to get organized, then the channels just go whacking straight out and they capture any other drainage further down the system. Does that make sense?
Yes, it does. But I'm also wondering about, does that imply that whatever sand and sediments were coming down through the J hook, that went away, that was diminishing, and these other systems took over?
Yeah, it does. Well, that's my interpretation, because interestingly enough, they cease to be active. They just get abandoned. Everything on that surface gets abandoned and then eroded on that eastern side. So yes, it kills that drainage. Whatever the first sets of drainage systems were, they're killed. That's it, doomed. So first off, that one on the east side takes over, then one on the west, and then ultimately there's a huge one that comes in all the way from the upper slope. So the upper slope is healed. So those two intermediate ones are aggradational, but they're still part of the healing process up dip. And ultimately there's one dominant one per Pleistocene sequence, and that dominates the whole of that interval. Yeah. So Weimer, Weimer's original work, those big channel complexes in the Pleistocene, they're dominantly the feature of the Pleistocene from then on. Yeah.
Okay, any other question?
Nice. Very nice questions. Good. Totally appropriate.
So
thank you, Stan. I'm sorry you lost contact halfway through, but yeah. Good.
More question to Gillian. Yeah, I think that's all.
Okay.
Yeah,
Thank you.
Thank you very much, Gillian. Hopefully you can enjoy your London life.
Oh, I always do enjoy my life. But actually,
okay.
I quite enjoy giving that talk. So thank you all for listening.
Yeah,
okay.
Thank you so much today. Bye-bye.
Okay, bye.
Thanks, Jill. Great stuff.
Hey, thank you. Thanks for coming back.
Bye.
Okay, I'll leave somebody else to end this because at the moment oh, there we go. There's the leave. Shall I end the session on my side? Thank you.
Sure.
Thanks,
Bye-bye.
Dan. Bye.
Have you gone, Jill?
No, I haven't gone yet. Hi, Greg.
I was just going to say hello. I had to
Good
keep
to
everything
see
mute.
you.
Oh, Frank is under the table.
Yeah, I didn't let him sit up at his desk chair because he would have distracted me. So he was in there playing his guitar, which of course I then had to go and shut the door on.
It wasn't really you performing, was it? It was a marionette controlled by
The glove puppet, yeah.
So yeah, Frank is of course still toothless, but ultimately responsible for an awful lot of that mapping, which is pretty stellar because it's not easy mapping up at the top.
The question I was going to ask, which I didn't bother in the end, was why were the colours on Frank's drawing so muted?
I'm not sure they were Frank's.
Were they not? I thought the line drawings might have been.
Yeah.
Maybe not. I just have,
Yeah.
recollections of psychedelic drawings in Frank.
He does actually normally do very psychedelic drawings, you're right.
They didn't like my fluorescent pens.
But I don't like them. Yeah.
Brilliant.
Okay, thank you so much.
I'm going to end
Thank
the
you very
recording
much.
right now. Thank
Okay,
you.
yeah, thank you.